Bismillahirrahmanirrahim. Assalamu alaikum everyone. Welcome to our thesis presentation. First of all, I would like to thank our Honorable Board of Examiners and Teachers for allowing us to present our thesis. Our thesis was supervised by Mr. Muhammad Mominul Haq, Assistant Professor of CE. Me, M. Jaman, along with other three group members, will present the thesis. Our presentation is divided into the following topics. I will present up to statement of the problem. Sabbir Ahmed will present laboratory investigation and data interpretation. Shoaib Ryan will present result and discussion, and remaining topic will present by Shwanur Rahman. Our thesis topic is the application of dynamic core penetrometer for the quality control of improved subgrade layer. The specific objective of this research are to develop relationship between dissipity below and dry unit weight, as well as dissipity below and relative density for improved subgrade soil. For any gives value of dissipity below, dry unit weight and relative density can be estimated from the relationship. The relationship can be used to control the quality of improved subgrade layer. Due to the poor quality of subgrade severe, most of the pavement works required an improved subgrade layer in Bangladesh. The improved subgrade layer is required to compact to the relative compaction of 95% and above compared to the maximum dry unit weight measured in the laboratory standard or Proctor test. After compaction, the quality is controlled. That means field dry unit weight is measured by means of sand cone method. But sand cone method is required both field and laboratory measurement. Hence, it is time consuming and uneconomic. On the other hand, dynamic cone penetrometer is the extensively used to estimate subgrade severe. That means extent of subgrade layer. The severe value is estimated from the standard dissipity penetration and dissipity below. The dynamic cone penetrometer is the simple and handle equipment, quite easy to operate compared to the sand cone method. It requires only field measurement, hence time saving and cost effective. So in this research, an attempt has been made to develop relationship between dissipity below for a specimen penetration depth and dry unit weight as well as relative density of improved subgrade soil, and relationship can be used for quality control. In this study, improved subgrade soil sample was collected from the bus rapid transaction project Gazipur. I request my next presenter Sabbir Ahmed to continue the presentation.
Thank you, MD Rashid Jaman. Now I continue this presentation. After sample collection, different tests were conducted for the determination of index properties, such as green size analysis, specific gravity, minimum and maximum dry unit weight, test by using gravity tables. Besides standard Proctor test were performed to estimate maximum dry unit weight and optimal moisture content. The data from index properties, index testing were used to prepare sample for dynamic combination test. The result obtained from the laboratory test are listed in the following tables. The collected soil is the poorly graded and having fineness modulus and a specific gravity of 1.52 and 2.66 respectively. Minimum and maximum dry unit weights were found 13.88 and 70.04 kN per meter cube from vibrator tables test. From standard Proctor test, maximum dry unit weight and optimum moisture content were found 70.0405 kN per meter cube and 12.15%. Were performed both vibrator table and standard Proctor test to estimate maximum dry unit weight of soil, because it is essential parameter for the preparation of specimens for dissipity test. Maximum dry unit weight obtained from both tests are almost same. For dynamic cone penetration test, specimens were prepared 90 to 100% of maximum dry unit weight obtained from laboratory test. The range 90 to 100% is selected because root construction. Specifications recommend more than 95% compaction in the field compared to dry unit weight obtained in the laboratory test. A 147.32 mm diameter and 304.8 mm. High mold was used for specimens preparation. The specimens were compacted in 6 equal layers and equal compacting effort using standard Proctor hammer, and targeted densities were achieved by trial and error. After sample preparation, the dynamic penetration tests were performed at each density to obtain number of blows required to prepare a depth of 152.4 mm. Top 76.2 mm was ignored because of lack of confinement. Next 152.4 mm depth was considered for penetration depth, which is enough to represent field condition. DCT were performed on 10 samples in the range of 90 to 100% relative density. In other words, 90 to 100% of maximum dry unit weight. The samples were prepared by increasing the density not more than 2%. The following graphs are representing DCP penetration various DCP blues in the range of 90 to 96%. The following graphs are representing DCP penetration various DCP blues in the range of 96.3 to 99%. And the following graphs are representing DCP penetration various DCP blue in the range of 99.3 to 100%. From the DCP blue various penetration plot, the DCP blue are estimated for 152.4 mm penetration. For this particular graphs, it can be seen that for 152.4 mm penetration, the DCP blue is 5.28. I am requested my next presenter Khondokar MD Sharif Raihan continue this presentation.
Thank you, Sabir Ahmed Bhuyan. Now I continue this presentation, results and discussion. Then the DCPT blows for 152.4 mm penetration are plotted against dry unit weight of the specimens to develop the relationship. From the graph, it can be seen that the DCPT blows per 152.4 mm penetration pursued a linear relationship with the dry unit weight, a high coefficient of determination of 0.9898. So for any no values of DCPT blows, the dry unit weight can be estimated from this graph. A similar relationship is also developed for DCPT blows with the relative density for the same specimens. From the graph, it can be seen that the DCPT blows per 152.4 mm penetration pursued a linear relationship with the relative density with a high coefficient of determination of 0.9899. So for any no values of DCPT blows, the relative density can be estimated from this graph. I am request my next presenter MD Shwanur Rahman to continue this presentation.
Thank you, Sharif Rahan. Now I continue the presentation. Conclusion. In this study, two relationships have been developed. One is DCPT blows versus dry unit weight, and another is DCPT blows versus relative density. Both are linear relationship with a high coefficient of determination, and it is expected that both relationship can be used for the quality control of improved subgrade layer. Recommendation. It was a laboratory-based investigation, so field study may be conducted to find out the validity and effectiveness of the correlation in future research. Also, how sample change can affect the correlation may be investigated. Acknowledgement. We would like to acknowledge Engineer Palash Ahmed Smith, Bangladesh, for providing the soil sample for this study. Also, special thanks to Mr. Ahadullah, lecturer, Department of Civil Engineering, for helping us with a minimum and maximum density test at Geotechnical Engineering Laboratory of Buet. Thank you for your patience and listening to us. If you have any question, please feel free to ask. We would love to answer.